both in electrical engineering. And with that, we're really excited to have you today for our presentation.
Yeah, thanks for the introduction, also the invitation to present. So today I want to talk about what does RL theory have to do with robotics? So this might be a slightly different perspective, I think, than the average sort of robot learning talk, but I hope it's actually an interesting one and may stimulate sort of um, further research. Okay, so just to kind of give some context for this talk, so during my PhD, I was mostly working on learning theory, sort of trying to understand like the sample complexity of RL and stuff like that. So my research looks a lot like this, doing math on whiteboards. And then over my postdoc, over the last couple of years, I've kind of switched to doing robotics research and trying to understand how do we actually get things to work on real world robots. Okay, and sort of kind of from a high level view, these might actually not seem to be super related, right? At least for those familiar with the literature, like there's not a whole lot of examples where RL theory has impacted robotics. And likewise, I think most theorists, maybe they have a picture of a robot on their interest slide to motivate what they do, but otherwise their sort of work is not necessarily really tied to sort of real world robotic challenges. But what I want to argue through this talk is that actually they're sort of much more connected than that. And that indeed, sort of there are real world challenges that thinking about them through sort of the lens of RL theory and maybe just more broadly kind of like fundamental algorithmic sort of paradigms actually provides insights that allow us to get algorithms that actually work in the real world and that are maybe sort of not obvious if we don't approach this from this more theoretical perspective. And likewise, sort of by taking sort of these real world problems, we can actually come to very sort of interesting and novel theoretical settings that we might not have gotten to before. Okay, so the goal of this talk, in some sense, I want to sort of work through or think through a couple problems that I've worked on, where sort of there are real world challenges we are facing on robots, and we kind of thought through these maybe from this more principled algorithmic angle, and we were able to get actual sort of algorithms through that worked on real robots. Okay, and so feel free to stop me at any point in the talk if anything's unclear. I'm happy to make this as interactive as possible. So, what is our broad goal here? Well, this is a robot learning seminar, so I don't need to say this, but sort of maybe the broad goal of the community is to get robots to do cool things, right? We want to have robots that are in the world that are doing useful tests and sort of using learning based methods to get there. Um, what is the challenges here? Well, the obvious challenge is that sort of doing this is very hard. Like learning these policies, learning robot policies from scratch in the real world is typically not feasible. The world's complex. We sort of need some other information. How do we usually think about doing this then in the robot learning community? And there's a lot of different methods and approaches people have applied, but I think sort of maybe two common or a very common way of thinking about it is we use sort of prior information about the world to sort of learn good policies that we could then run in the real world. And what does this prior information looks like? Well, sort of broadly, this is not the only options, but two sort of standard ways we might approach this is we'll use simulators, so learn a policy in a simulator and sort of transfer this to the real world, and sort of use human demonstrations, right? We have a human demonstrate on a robot what to do, and we can sort of train a policy with behavioral cloning or something, right? And so sort of broadly, I think the robot learning community has we see lots of papers sort of approaching it through one of these angles, trying to learn good policies using these sort of sources of prior information to enable sort of real world robotic capabilities. Okay, but the challenge, of course, even with this, is that our priors are never perfect, right? Too often in sim to real transfer, we'll train a policy in our simulator. Maybe it works in the simulator, but we deploy this in the real world and it fails. With human demonstrations, sort of what we often observe is that the human demonstrations are themselves not good enough, right? So this is sort of a common observation actually in a lot of different works in the robot learning community. Even as we scale the number of human demonstrations, the sort of success rate stays at like 70-80%. Okay, so human demonstrations alone are maybe not sufficient. Okay, and so while it's absolutely critical in robot learning, like I guess if we want to get policies to work in the real world, we need sort of prior sources of information to learn good policies. Often the prior sources of information that we use are still not good enough to get us like all the way there. We want truly reliable policies that succeed 100% of the time, and sort of the way we have of training policies currently often doesn't get us there. Okay, so how do we get there? How do we get policies that is sort of, succeeding as much as sort of as much as we would like? And I think again, there's different ways we could approach this, but a very sort of common way or promising way we might do this is to use reinforcement learning, right? So maybe I can take a policy trained on a simulator, I can take a policy trained on human demonstrations, and I can apply RL to that policy in some fashion, and I can get maybe something that succeeds at a much higher rate, right? And so this is maybe like just a broad paradigm we can think about of learning things and simulators and demonstrations, getting some initial starting point, and then using RL to actually get us the rest of the way there. Okay, and I think we see lots of examples throughout the robot learning community and sort of broadly applying this sort of a paradigm, right? And then this introduces sort of many questions as we start to think about how to actually instantiate this, right? What is the best RL algorithm to use? Do we need to run RL in the real world at all to get sort of this improvement? Is online RL required? Can we use offline data? Et cetera. There's sort of an endless list of questions we could ask about how to sort of actually make this paradigm work. And I've worked on a variety of these questions, but sort of the question I actually want to talk about today is maybe a little bit more fundamental and upstream of sort of any of these particular questions. And that is, how do we actually utilize the prior information, whether this is a simulator or demonstrations, to obtain a good initialization for further RL improvement, right? If we know that sort of the prior information is maybe not good enough to get us all the way there and we have to do some further RL, how do we think about sort of using this prior information to ensure that that is a good initialization for RL? Okay, so this is sort of going to be the like motivating question in some sense of the talk. How do I use priors to do RL? And again, I want to think about this maybe from a slightly more theoretical angle than we would usually approach these questions in sort of robot learning, but then show that through that we can actually get practical real world algorithms. Okay. And so maybe the two sort of framing questions of this then is first, can theory help us understand how to best use this prior information that we have? And secondly, um, if so, can theory then actually lead us to more effective real world algorithmic approaches? Okay, so that's going to kind of be the framing of the talk. Um, I'm just, I guess, sort of a few just like notational preliminaries. I'm going to assume my environment, I'll denote it by script M, is some Horizon H Markov decision process. Throughout this talk, I'll denote JPi to be the expected reward of policy pi. And, so standard RL setting, our goal is just going to be to find a policy maximizing JPi. Okay, so JPi is just, we have some reward that quantifies whether or not we succeed at the task. We just want to find a policy that in the real world succeeds at the task. Okay. Um, okay, and so I'm going to talk about this in two parts. First, I'll talk about how do we think about using simulators, pre-training and simulation to enable online RL improvement, and then I'll talk about sort of how do we actually pre-train from demonstrations to enable online RL improvement. So before I dive in, any sort of questions that anyone has on the sort of like framing of the talk or motivation?
Think I'm
Okay.
good. And maybe one really quick thing.
Yeah.
Uh, I guess I'm just wondering, because I'm curious about this question too, but also how much this question might change a little bit depending on the like abilities of the prior. Like when you
Yeah.
use a different R algorithm. So I think you'll get to this at the end though.
Yeah, this will come up a lot in the talk. The details of sort of the actual RL algorithm we use, I'll be a little bit agnostic in this talk. This is certainly important, but I think the questions that I'll try to answer are like even actually a little bit upstream of that. So I think sort of it'll become clear as the talk goes on. Yeah,
Okay.
but if
Yeah.
not, feel free to ask me more.
Okay, great.
Um, okay, so let's start with this question of simulation. So how do we pre-train a simulation to enable online RL improvement? Okay. So what is this sort of setting here? Okay, we have a real environment. We want to do some task on our robot, maybe pick up a beam and set it in blocks. And we have some simulated model of this environment. Okay. Our goal, of course, is to get a policy that solves a task in the real world. And what we'll assume is we have sort of access to the simulator as much as we want. Like I can sort of run anything in my simulator. And this is sort of like fairly cheap and inexpensive. So samples from my simulator are effectively free. That's sort of the good part here of having the simulator. The obvious issue is that, you often have, and this is especially true maybe in robot manipulation settings, you'll often have some fundamental mismatch between the sim and real. So too often, if you take a policy that you learned in your sim and you transfer it to real, you're not going to get actual perfect transfer. Okay. Um, and so to sort of approach this maybe a little bit more theoretically, I want to understand how do we, this is maybe sort of a practical setting This is sort of the real world setting we have. How do we abstract these features into some more mathematical setting that kind of preserves the key features of the setting without being sort of theoretically intractable? And then if we can do that, how do we sort of think in that setting what the right approach is to do and transfer this back to the real problem we're facing? Okay, so I want to try to formalize a sim to real setting in a way that kind of preserves the key features of it. Okay, and so what are the key constraints? Well, again, constraint one is maybe that the dynamics of sim and rail do not match perfectly. This is kind of fundamental. Constraint two, and I mean, this isn't a constraint, it's a good thing, and that policy optimization in sim is effectively free. I can run my favorite RL algorithm in sim, and usually this, maybe this is not completely trivial, but like usually this will work if I tune my RL algorithm right. And then what I want to also add this last constraint is that in real, either we can rely on a policy I learned in sim, so I can take a policy I learned in sim and place on real, or I can rely on what I'll call simple RL algorithms. And I'll define shortly what I mean by that, but sort of intuitively, this just means, the kind of algorithms we actually are running in practice. Okay, so given kind of these features, how do we formalize this into some mathematical setting? Right. So first, the dynamics of sim and real do not match perfectly. For this, I'm going to make actually a pretty simple assumption on this, and all I'm going to assume is that if the transition dynamics are real, of real are denoted as p real, and of sim are denoted as p sim, then the sort of total variation distance, for those not familiar, this is just some distance, similar to KL on two probability measures, is upper bounded by some value epsilon sim. Okay, so there's some factor epsilon sim that says that every state, the difference in the dynamics between sim and real differs by no more than epsilon sim. Um, and this is a pretty coarse, actually, way to formalize this, and it's probably certainly not the actual mismatch we have between sim and real. Like it might be much more sort of nuanced. But I actually want to, what I'll sort of argue is this is sufficient to actually understand what we should do. So this is what I'll assume for the mismatch. Sim and real sort of can differ, but only by a most effective epsilon sim. Policy optimization in sim is effectively free. So for this, I'll just assume I have sort of a policy optimization oracle. For any reward function r tilde, may or may not be our true reward, I can compute an optimal policy in MSIM for R tilde, right? I can run PPO, SAC, whatever your favorite RL algorithm is, and sort of I'll assume this works. And then this question of sort of simple RL algorithms. So in real, we can only rely on similar policies or simple RL algorithms. For this, sort of in a theory sense, what I'm going to assume is that in real, what I want to sort of restrict myself to is regression oracles. Okay, so given some Q function class, this will just be a neural network class in practice, I can fit a Q function class using sort of regression. Why is this an important restriction? Well, sort of in theory, when we write down theoretically sort of provable algorithms, often we use much more complex exploration procedures than what we can actually implement on our robots. And so I'm kind of trying to get away from that. I want to say I want to restrict myself to algorithms that I can sort of actually practically instantiate. And I can do this. I can run sort of square loss regression. And indeed, most RL algorithms we use, SAC, etc., they kind of rely on some form of squared loss regression. So this is sort of the formal assumption, but really this is just trying to get out what is the algorithm I'm actually going to run, rather than running some sort of complex theory algorithm that's not really implementable. Okay, so these are kind of the formalism of this sim to real setting. I'll need just a couple extra assumptions. This is more technical, so I'm not going to go into detail on this. I'm going to assume that my MDPs are low rank MDPs. That basically just means that you can have some linear decomposition of the transitions. Again, in practice, the world is probably not a low rank MDP. But I guess what I'll argue is that by introducing this formalism, this still gives us enough expressivity to understand what the right thing is to do for the real world. Okay, so we assume sort of we have this low rank MDP structure, and our goal, of course, is to find an epsilon optimal policy uh, in Embryo. Okay, so this is going to be the formal setting we're going to consider. Basically, this you can just think about as sort of a mathematical formalization of the sort of sim to real setting that we would actually encounter in practice. And what I want to do then is I want to understand in this formal setting, sort of does standard sim to real transfer, which I'll define shortly, does that work? And if not, kind of what are the failure points of that? How can we do better? And then sort of once we understand this in the theoretical setting, can we transfer that to a real world algorithm that I can actually run on my robot? Okay, so that's going to be kind of the plan of where we're going in this. Okay, so first let's understand, is standard sim to real transfer sufficient? Okay, standard sim to real transfer I'm going to define as the following. I use my policy optimization oracle to find an optimal policy in the simulator, right? A policy that solves a task in the simulator. I play that policy in real. Maybe I do some sort of random exploration from that. Maybe I do some RL fine tuning. But the basic thing is that I take my sim policy, the policy optimal in sim, I play this in real, and I sort of maybe do some RL on it. So some sort of lightweight RL on it. And this is kind of broadly, I think, how we usually maybe would do sim to real transfer. Maybe we do some domain randomization in the simulator. There's various other tricks we might do, but sort of this kind of encapsulates conceptually what standard sim to real transfer looks like. Okay, so the first question is this sort of provably efficient? Does this approach make sense? Okay. Um, and so we can actually say in this sort of more formal setting that let's say there exists three MDPs, there exists a simulator and two different real environments such that both the real environments are consistent with the simulator in terms of this sort of epsilon sim mismatch assumption, but they have different optimal policies. And if I run the above procedure, it'll require exponentially many samples for me to identify an epsilon optimal policy, epsilon sim optimal policy in one of the real environments. Okay. Um, and so basically what this shows is that this sort of standard sim to real transfer is sort of exponentially bad. Like if I want to actually prove something about this, you can't prove anything more meaningful than say, oh, I get an exponential complexity guarantee. For those sort of not familiar, exponential scalings in learning theory is very bad. This basically means it's not learnable. Right. So this is a very negative result on sort of standard sim to real transfer. And this is actually tight. So what you can show is that under my sort of transfer assumption, I can get an epsilon sim optimal policy by directly transferring it, but I can't do better than that. Okay. Um, I think I want to understand. So it's important actually to understand here why this breaks, because as we understand why this breaks, it'll actually allow us to see what is better. So I want to go over the example that kind of allows us to prove this result. And it's actually incredibly simple. So the example where central transfers fails that we came up with is the following. So I have a simulator that has two states, so denoted by red and yellow, and two actions denoted by black and blue. Every transition is deterministic, except for the last transition. So if I get to this state, and I take the black action with some probability, I transfer to state S1 and I get a reward of 1/2. Otherwise, I transfer to state S2. Reward is 0 everywhere except at this state, where I get a reward of 1/2, and in all of these transitions where I get a reward of approximately 1/8. Now, if I can get to the end and get a reward of 1/2, this is sort of better, right? Like if I take one of these actions and get a reward of 1/8, then I'm sort of stuck in the state S2 and I get no further reward. So it turns out the question of which policy is optimal comes down to simply the weight of this transition. If this transition is it's sort of if I take the black action and I'm fairly likely to transition to this state, then I can get a reward of close to 1/2 by just playing the black action the whole time. If that's not the case and this transition is very small probability, then I should just take sort of a blue action and get a reward of 1/8. Okay, so you can tune this environment such that the optimal policy in sim is actually you take the blue action, collect a reward of 1/8, and then you sort of follow that path. You're stuck in S2 the rest of the time. Okay, so the real environment here I'm going to construct is identical to this environment. The only difference is the transition probability at this last state. So now basically the probability of getting to this state is higher in real than it is in sim, and it's higher enough that actually the optimal policy in real is now actually to play the black action every time, right? To get to this state of 1/2. And so what we see is that because we can, even under sort of a small perturbation, just perturbing this last transition, we can sort of drastically change the optimal policy. And we can change it in a way that is very sort of negative in sim, right? Like if I take the optimal policy in sim and I deploy this in real, I'll get stuck in this state S2 and I'll never actually get to this last state that says, that will tell me, I can actually collect a reward of 1/2 in real. And so by playing the optimal sim policy, I can't actually learn anything truly useful about real. I can't learn what do I want to learn in real? I want to learn in real whether or not this transition, whether or not I can easily transition to the state that gets a reward of 1/2. Okay. By playing the sim optimal policy, even if I add in some random exploration, the probability of ever reaching this state and learning something about this transition is like exponentially small. Okay, so that's kind of why you get this separation because the sim optimal policy can sort of be catastrophically bad or catastrophically uninformative when we deploy it in real. Okay, but what can we say actually about the simulator in this setting? How could the sim help? And what we observe is that in this example, another thing I could do is if I let's say I took a policy for my simulator that the goal of this policy was not to be optimal, but just to go to a state, right? It was just go to state S1, then this policy actually transfers perfectly, right? There's actually no difference up to this point. So if I just tried to get to this state from my simulator, and I'd play this in my real environment, I would get to the state in my real environment. Okay. And sort of the key insight here is while the optimal policy could differ substantially from sim to real, the behavior of any fixed policy cannot differ substantially. And sort of formally it can differ at most by a factor of epsilon sim. And so if I take a set of fixed policies in my simulator, right? Policies that are not trying to necessarily solve the MDP, but just trying to traverse the MDP. I can actually transfer these policies effectively. I don't have sort of this catastrophic difference in the behavior of these policies, right? And so kind of the question here is then maybe instead of using my simulator to learn an optimal policy like we usually do in sim to real transfer, I should be using my simulator to learn an exploration policy. I should be using my simulator to learn a policy that enables me to sort of traverse the MDP. Okay, are there any sort of questions on this example? Okay, if there's no questions, then I'll keep moving. So this kind of then motivates a fairly simple algorithm. So let's train policies in my simulator that instead of trying to be optimal, try to get high coverage, try to explore in my simulator. Okay, turns out I can implement this using only the sort of policy optimization oracle I've got in my simulator. Then what I'll do is I'll take these policies, the policies I learned in my simulator, the exploration policies, I'll deploy them in my real environment, and I'll collect data with these policies in the real environment. And then I take that data and I use my sort of simple RL algorithm, this regression oracle, to learn a Q function on that, and then I learn some policy that maximizes that Q function. Okay, so the idea is that instead of using my simulator to learn an optimal policy, I can use my simulator to learn an exploration policy. I can use these exploration policies to collect useful data in the real world, and then I can use that data to actually learn an optimal policy in the real world. Okay, and what can we say about this? Well, we can say that as basically we prove the following: that as long as your epsilon sim is small enough, so you still need your simulator to be sort of close-ish to the real environment, with high probability, the algorithm here requires only polynomial number of samples from the real environment to sort of learn an epsilon optimal policy. So we have this separation where direct sim to real transfer requires an exponential number of samples. Our approach of exploration policy transfer requires only a polynomial number of samples. So we get this exponential separation between using our simulator to learn an optimal policy versus using our simulator to learn an exploratory policy. Okay. So this is really nice, and like we sort of understood something theoretically about this, but is this actually useful in practice, right? Sort of are these this idea that we said sort of, okay, so mathematically, we can show that using your simulator to learn an exploration policy is better. Is this actually better in practice? Okay. And so what I want to do is think about how do we take this idea, this theoretical idea, and distill this into an algorithm that I can actually run. Right. And the key idea behind the algorithm is I want to train a policy that achieves high coverage in my simulator, transfer these policies to real, and use the data I collected to real to learn the correct behavior. That's kind of the conceptual idea behind this theory. And so we can take this sort of theory algorithm and say, okay, the first step is train policies in your simulator to cover the feature space. So all that we're gonna replace that with is just train policies to attempt diverse behaviors in your simulator. There's lots of sort of like deep RL algorithms that do something of this flavor. Okay. The second step in this sort of theory algorithm is play the policies in your real environment and use this data to collect data. Okay. We can just easily implement that. We take the policies we learn, these sort of diverse policies we learn in sim. We deploy these in real and we collect data with this. Okay. And then this last step is use a regression oracle to learn a Q function. For this, you can just basically take the data you collected with these exploration policies and incorporate them in your favorite off policy RL algorithm. In practice, we use some SEC. Okay, so this is kind of the practical instantiation of this theory idea. And then the question obviously is this, does this work? And it turns out it actually does. So right here, sort of some quantitative results where we see the performance of our algorithm in blue, the performance of direct policy transfer in orange on some simulated environments, and we see that indeed we can actually learn much more quickly. Um, and then we took this and we sort of implemented these ideas on a real robot. In this first example I'm going to show you, the goal is to push a puck to the edge of the table. So a very simple task, but we see that standard sim to real transfer, which is what I'm showing you here, doesn't really work. It kind of gets stuck. There's sort of enough of a mismatch that transferring the sim policy doesn't enable you to learn. It doesn't enable sort of effective performance in real. Now, I learned a set of exploration policies in the simulator, which is what I'm illustrating here. And you see that they're kind of doing a lot of things, kind of pushing the puck around in different directions. But the point is, like, even if these are not solving the task, they're collecting sort of useful information about how we can solve the task about how the real world behaves. And then what I do is I took that data and run SAC with it, and I learn a policy like this that actually does solve the task. Okay, and so more quantitatively, we can see this is sort of the learning curves in real. That as we sort of uh, if we do this exploration policy transfer, when we deploy this in real with RL, we can get sort of significantly better performance over time, whereas sort of doing RL fine tuning on the policy we got for direct sim to real transfer fails. Um, Here's another example. The setup here is a little bit different. Instead of running SAC, we actually sort of use our simulator to kind of uh, learn a little bit more directly, but the kind of conceptual idea here is the same, in that we learn exploration policies in our simulator and deploy those in real. The goal here is to stack the beam on the blocks, and we see the same performance. Whereas if I try to do direct sim to real transfer, what I have here, it fails. Where if I use exploration policy transfer, I can use the information I collect in real to actually learn successful task solving behavior. Okay, and so maybe the takeaway from this is just that, we formalize the sim to real setting, we sort of derive mathematically something about how we should think about it, and then we deploy this in the real world, and what we found is the algorithm we got from this sort of mathematical analysis actually gives us capabilities in terms of understanding how to use a simulator that help us learn policies that solve tasks that sort of standard approaches to sim to real transfer were not able to learn. Okay. Um, Before I move on, so that's kind of the first part of the talk, thinking about how to use simulators. Before I move on to the second part of the talk, are there any questions on this simulation transfer part?
Yes. So to be clear, for what you've done, you've essentially shifted the I guess exponential exploration um, from like the learning space into having like exponentially, or I guess combinatorially huge exploration in the state space. Is that correct? Like
Um,
you now want to explore the entire state action space and then have those examples in your simulator?
so I guess the way to think about it is, to like maybe if I go back to show the visualization of the exploration policies. Um, So these are the exploration policies we learn. Learning this behavior is sort of non-trivial in some sense. Like if I wanted to learn even this behavior from scratch in real, I still need to learn how to move the robot, how to move towards the puck, all of these sorts of things. So kind of the idea is I can learn these sort of behaviors in a simulator, and these behaviors actually will transfer. And kind of this makes sense in that, like, if we look at what it's doing here, it's quite simple. It's just trying, like, all it needs to do is kind of poke at the puck, right? It's a sort of easier task than the maybe precision we need to actually like push the puck to a goal. So I can learn to sort of learn these very low precision, but maybe like informative behaviors in my simulator. And then when I deploy those behaviors in real, I can use the data that is sort of collected by them to get a much more refined understanding of how the world behaves and actually learn an optimal policy in real. Now, if I were to try to do this with, say, learning from scratch in the real world, even learning this is probably infeasibly difficult because um, I need to learn how to like move a robot towards a puck. This is sort of like non-trivial if I don't have any prior information, but I can transfer that part of the learning to sim, and then I can use the information I collect from that to actually learn a policy to solve my task. Does that answer your question?
Uh, kind of. So my question is kind of stemming from 2 points. First, I want to understand like how similar would this be to something like diversity is all you need, where you essentially just want to find very diverse policies. Um, but in diversity is all you need, you're more looking at like state or trajectory wise diversity. And it seems to me like that is kind of what you're looking for here as well. Like you want
Yeah.
coverage of the state space or the trajectory space, let's say, rather than just stochasticity in your policy itself. Although it
Yeah.
does sound like you're using self-vector critic as well, so maybe that helps
Yeah.
exploration or process-wise. And then the second part of, I guess, my curiosity here is if you, I guess, take the or the, you know how you said your initial theoretical sim to real transfer result had an exponential explosion essentially.
Hmm.
Do you basically mitigate that exponential term by transferring the, or by essentially having transfer learning only between um, like any given policy and like a one-step Q value estimation? So like in essence, you're getting rid of the exponential part in the bound, and then you're just um, I don't know what sort of concentration inequality you're using, but
Hmm.
I assume that the concentration is now just on the Q learning rather than on exploration plus Q learning. And does
Yeah.
that help?
Yeah. Yeah. So to answer your first question, actually, in terms of how do we implement this first step, train diverse policies in SIM, we actually use the diversity is all you need algorithm or like some like mild variant of that. But it's sort of conceptually, that's conceptually actually exactly what we're doing. The insight is like you should be running that diversity inducing thing in your simulator to get policies that do diverse behaviors in real that allow you to learn. So that's kind of maybe an answer to your first question. And then on top of that, we do run SAC in the real world. And that stack is initialized with sort of the sim weights, the weights you learn in sim, which I think is probably important, but it's not sufficient. Like it actually is critical that we do like if you look at the learning curve, it's actually both of these are kind of initialized with SAC weights that we're learning sim, but it's critical that we run these diversity is all you need policies to explore. Um, so I guess that's maybe the answer to your first question. To the second question, so what I guess the theoretical result relies on is you can show that. So if you go back to this example that I motivated things with, basically okay, well, what do you want to do here? The key thing is you want to get to this last state. If I get to the only difference between sim and real again is this last state. If I can get to the last state, then I can learn, okay, this, this transition is, um, high probability or low probability, and that tells me what my optimal policy is. So the key thing then in terms of learning in this setting, at least from sort of like a sort of information theoretic perspective, is that I need to get coverage over my states. I need to get to this state such that I can collect information from it, and from that I can learn. And so what we can show theoretically is that when we transfer these sort of exploration policies, they give us coverage. Like they'll let us get to the states we need to get to learn what actions we should take. Once you have coverage, so then you can get a theoretical result that says, if I run these policies I learned in sim that explore in sim, if I run these in real, they also induce effective exploration in real. So sort of more formally, they give coverage over the sort of feature space of my linear MDP. Once you have that, you can actually just directly use that to show that learning with this like regression oracle will actually succeed. Um, but the key thing here is just data coverage. So you can basically say using my sim, I can get policies in real that will give me will induce like high data coverage in real.
Okay, okay. It's super interesting. I find it's really cool that you're using diversity is all you need in I guess simulation to cover all these, I don't know what you call them, modalities or different
Yeah,
behaviors. Really interesting. All right. Thank you very much.
yeah,
Okay.
um,
I'll just ask a really quick question, Andrew. That's all
yeah.
right. I
Go
mean,
for
this is a little bit about the error bound. So is that uniform over all like states between the sim and the real environment?
it. You're talking about like the assumption we made. Oops.
Yeah.
Like this here.
Yes. What's the
Y-
TV bound? Because I
Yeah.
guess
So
yeah, go ahead.
yeah. So we do assume this is uniform over all states in your real environment. So obviously this is probably not true in practice. Um, but this is it.
Yeah, but that might also, okay, good. Yeah,
Yeah.
because there might be some cases where like most of the error is in like the state right around where the awesome goal is, if I want to be
Right.
an annoying adversary. But
Right.
maybe
Yeah.
it's
Yeah,
also good
maybe
to,
like if you're moving through free space, like there's actually very low mismatch because it's easy to model that. When you have contact, it's like high mismatch,
Mhm.
So it's definitely not perfect. I guess what I kind of the way I think about this is just like um It's not perfect, but even doing analysis under this assumption helps us to understand like a reasonable approach. So that's still sort of a lossy assumption, but it's sort of lossy in a useful way, in that it preserves the key feature.
Hmm. Yeah. Well, I think it's also informative too for people building world models. Maybe they should aim more for uniform error across the world model if they can, because at least it aligns with the theory better.
Yeah, I think that definitely is an interesting question about how this would actually think direct how you should like learn a model. That I think is like, yeah, would be very interesting to explore.
Okay. Yeah. Thank you.
Yeah. Okay, so maybe I'll move on to the second part of the talk. Um, I'll try to go a little bit more quickly through this. So in this first part of the talk, we thought about how we can pre-train in simulators. In the second part of the talk, I want to think about how we can pre-train from demonstrations. And I'm going to kind of follow a similar
I have
pattern.
another question, actually.
Oh
If
yeah,
you could,
Can you hear me? Sorry.
yes.
Okay. Uh, so my experience with the like algorithm like stack in simulations for like task like locomotion was like if we want to explore and if we don't restrict the like for example the state space, it wouldn't converge to any reasonable policy. So what
Mhm.
people do is like restrict the state space and then so you wouldn't have that much coverage. I don't know if you had the like same experience. How did you
Yeah.
manage it?
Right. So yeah, how we actually do this in practice is so as I said, we ran this diversity is all you need algorithm. We run what we actually optimize is sort of a weighting of the diversity is all you need objective and just a standard RL reward objective. When you do that, that induces policies that you can think about as giving you like diversity around like reasonable task solving behaviors. So that there is you do need to practice some sort of restriction like that. Otherwise, you would just learn, you might learn a very diverse set of policies, but most of these are not pushing the puck. So you kind of restrict you incentivize your sim policies to be high diversity with diversity is all you need, but then also to do kind of reasonable things by adding in a reward maximization term.
Thank you.
Okay. So, uh, so for the second part, I want to talk about sort of a similar question, but now instead of my prior being a simulator, my prior is going to be some demonstrations, right? And so what is this? What does this look like in practice? Usually this means like we have a human, they demonstrate some set of tests on their robot, and then typically what we'll do is we just take those demonstrations and we train a policy to sort of copy them using behavioral cloning. Okay, so again, our goal is to find a policy that solves a desired task in the real environment. What we'll assume is that we're given some data set of states and actions from the human demonstration. We had a robot state, the human took this action in this robot state. And as in this in the real setting, we want to understand how do we abstract these features into more mathematical interpretation. Okay, so the key constraints here, the first constraint, again, we have this human demonstration data set. The second constraint I'm going to add is that I only want to pre-train with supervised learning. Okay, so there's lots of, if you give me a data set, there's maybe a whole lot of things I could do with this in terms of like offline RL and these more complex approaches. And I think there's a lot of validity to the approaches, and like we should be exploring them. But I guess what we actually see people doing in practice that seems to scale really well is we use supervised learning, right? We train a policy just to copy the demonstrations, and so I kind of want to restrict myself here to these sort of approaches that we've seen scale very well in practice. So I'll limit myself to only supervised learning. The third point then is kind of the key goal of what we want to do here again is we want this policy to be a good initialization for RL improvement. And the way I'm going to think about that is just that if I take this policy that I trained in my demonstrations, I roll this out a bunch of times in the real world, how can I ensure that the data collected from that is useful for improvement will actually enable me to improve. And so I'll discuss actually what that means in a second. Okay. So again, let's formalize the setting. We have a data set of human demonstrations. We'll just assume this is generated by some sort of idealized demonstrator policy. We can only pre-train with supervised learning. So for this, I'm going to assume we can use some sort of supervised learning oracle, some log loss behavioral cloning that says, I can fit the demonstrations, right? And in particular, I will assume that we have access to a generative model here, so I can fit not just a point estimate, but truly a full distribution, and it'll sort of become clear soon why this is important. And then here, this is maybe the key assumption. So it allows for RL improvement by simply rolling out the pre-train policy. So how do we formulate something like that? Well, what I'll formulate this as is that the pre-train policy, which I'll denote as pi pt, that we train on the demonstrations, I want this to support all the actions the demonstrator plays. Okay, so I want it to look something like the following. In every state, the sort of probability the pre-trained policy plays some given action is lower bounded by some scaling factor gamma times the probability the demonstrator plays a given action. Okay, in some sense, this is the minimal assumption we might hope to meet. So I'll explain actually through an example shortly how if you don't meet an assumption like this, when you take your pre-trained policy and you roll this out on the real environment, you might fail to collect the information that are sort of is required for RL improvement. So if we want to have a policy that's a pre-trained policy, if we want our pre-trained policy to be sort of fine-tunable in some sense with RL, even up to the level of the demonstrator, we actually need an assumption, something like this to hold. Okay, I'll explain this in a second. We also need some sort of structural assumption. What I'm going to assume here is actually that my MDP is tabular. Okay, obviously the real world is not tabular, but I think just like in the sim to real setting where I make this assumption, say on the mismatch or whatever, the point here is not for me to perfectly model my real environment with a theoretical setting. The point is to preserve enough of the key features of the environment that the algorithm I get here is actually useful in the real world. So these are very sort of different goals in some sense, and what I'll argue is that actually the tabular assumption is sufficient here. Okay. The last thing I'm going to add as a constraint is, in addition to wanting my pre-trained policy to have coverage over actions, I also really want this pre-trained policy to be good, right? If my pre-trained policy is just causing my robot to flail randomly, maybe this plays every action, so it kind of meets this coverage condition, but this is obviously totally useless. And so what I actually want is also my pre-trained policy to do reasonable things, say at least at the level of what the BC pre-trained policy would do. Okay, so the first question that we might ask under these assumptions is BC a sufficient initialization or fine-tuning? Okay, BC, this is kind of how we usually pre-train. All this is again, we take states, we train a policy to predict the action that the human played at a given state. Okay. Does BC satisfy sort of my desiderata? So what we can show is that there exists two MDPs such that for both of these MDPs, there does not exist in the policy and the support, there doesn't exist a policy in the support of the BC policy such that I can basically get to within epsilon optimality of the demonstrator policy. And this implies basically that we cannot identify an optimal policy in one of those by rolling out PyBC. Okay, I'm not going to dwell too much on the formalization of this or this statement because it's actually more informative, I think, to actually just see the example. Okay, so why does standard BC fail? So let's say our demonstrator policy looks like the following. Okay, so I have a simple MDP again. I'm going to start in some initial state with probability epsilon I transition to state S1 with probability 1 minus epsilon I transition to state S2. And my demonstrator, in state S2, they always play the blue action, and they state S1, they play the blue action half the time and the green action half the time. Now, let's say I collect a data set from my demonstrator in this environment. Now, if epsilon is sort of small-ish, then the probability my demonstrator goes to state S1 is not incredibly high. And so I might have a lot of examples, might have a lot of samples of them playing the blue action in state S2, but I might just have very few observations from state S1. And indeed, I might be in a situation where I just don't observe them ever play the green action because I don't have that many observations from state S1. So if I take this demonstration data set and I fit a BC policy to it, the BC policy is going to look something like the following. I'm only going to play the blue action in state S1 because I only observe that, even though my demonstrator would play the green action. Right, so sort of maybe more conceptually, the BC policy in a way overfits to the actions in the demonstration data set, especially if we have limited observations. Now, if we're in a regime here, say the green action is actually important, like maybe in state S1, the green action is actually better than the blue action, then the policy I learned with BC doesn't support all the actions I need for improvement. I basically can't guarantee that the BC policy will play the actions, in this case, the green action that is necessary for me to actually improve this or to sort of collect the information, right? So if I play this in my environment, if I roll out the BC policy, I get to state S1, I always play the blue action. I'll never observe the green action. I'll never observe that the green action actually is better. Okay, so RL fine-tuning in some sense in this case will not succeed. Now, there's an obvious fix to this. What I can do is the following, and this is sort of maybe broadly what we do in practice. I can take my BC policy and I can add some noise to it, right? At every state, I can perturb the action it's produced, with some small amount of some small random perturbation, and that will ensure that actually, indeed, at state S1, I do play the action, this green action, and then sort of from this, then I can, get some observations from the green action, and I'll learn the green action is best, and sort of RL fine tuning will succeed. So why is maybe this not the best option? So we can show formally here that to ensure that something like this preserves the optimality of the BC policy, the coverage actually, the random exploration is going to look something like this. Okay. In other words, there's some fundamental trade-off between random exploration and the optimality of the policy. In particular, at state S2, right, we have a lot of observations from state S2. We know exactly what the demonstrator is going to do there. So if we add some entropy, if we add random exploration of the policy at state S2, this is likely to cause us to be a lot worse than we would be if we just played the BC policy. Right. So at state S2, we can only play a very small amount of exploration, or we make our policy much worse. At state S1, we really do want to explore more because we want to try the green action, because we don't know what the demonstrator is actually going to do there. But preserving optimality requires that we really scale back the exploration weight. Okay, and so, BC alone is not going to doesn't give us sufficient coverage to enable RL improvement, but also BC plus random exploration likewise sort of has this fundamental trade-off in terms of its ability to give us coverage while preserving optimality. So, sort of in other words, the way we think about pre-training is insufficient, it is not good enough to obtain a good initialization for RL improvement. Okay, what would I actually like here? Like, what should be the goal? So if we think about, again, this situation, what I want in that state S2, I want to play very small amounts of noise or no noise, right? I know what the demonstrator is going to do there. I have all these observations. I'll just do what the demonstrator does. At state S1, I want to play a lot more noise, right? Because I don't really know what the demonstrator is going to do there. I don't have a lot of observations. So this is kind of what we would ideally want okay. And so the key insight here is actually that if I have a policy like this, if I add entropy to the distribution proportional to my uncertainty of the demonstrator's behavior, I don't actually increase policy suboptimality. Right? In other words, at state S1, I only have one observation, so I'm quite uncertain what the demonstrator would actually do in that state. Because of that, if I add some entropy to the distribution, it doesn't actually increase the suboptimality relative to what the BC policy would do. Maybe the BC policy is good, maybe it's not. I don't really know because I don't have observations. Right? So adding noise there doesn't hurt performance. Adding noise at S2 would hurt performance because I actually know exactly what the demonstrator would do there. Right? And so I kind of want to add my noise adaptively based on how certain or uncertain I am about what the demonstrator does. Now, it turns out, I'm not going to go into the full formalization, but it turns out that what you can show is that in sort of a Bayesian sense, what I have here, this policy I have here, is actually precisely the posterior of the demonstrator's behavior given D. Okay, and so the takeaway from this is actually, in some sense, rather than just doing BC, fitting the observations directly, I should take into account my uncertainty, and I should fit a policy to the posterior of the demonstrator's behavior. And indeed, we can show formally that if we do that, we get a policy, which we call the posterior demonstrator policy, that's no worse than the BC policy. So it performs as well in terms of sort of pre-trained performance, but it ensures you get actually this sort of nice coverage guarantee in terms of the actions. Okay, and you can actually show this is effectively unimprovable, that out of all policies that preserve the optimality of the BC policy, this is approximately the best coverage guarantee you can get. Okay. I'm running low on time, so I'm just going to quickly go through the rest of it. Turns out you can implement this fairly easily in sort of standard BC pipelines. We use sort of an ensemble-based approach to estimate the posterior, estimate the uncertainty. We can train sort of a diffusion policy then that widens the action distribution based on our uncertainty. And it actually works, right? So here I have a lot of simulated results that says running various RL algorithms on different simulated benchmarks, we see significant performance. That's in blue. Our algorithm is blue over fine-tuning, say, standard BC pre-trained policies, which is in pink. But I think actually what's really interesting here is when you compare pre-trained performance to fine-tuned performance. Okay, so This is average over like a significant portion of the Libero benchmark. We see pre-train performance on the left of our approach versus standard BC is effectively identical. You actually do get the same pre-train performance if you add noise in this way. But if you look at fine-tune performance, our approach is significantly better. So we can significantly boost our performance with fine-tuning, while BC mostly gets stuck when we try to fine-tune this with RL. And this actually scales to the real world. So here we ran sort of on a real world task. The goal is to pick up the corn and set it in the pot. On the left is the BC pre-train policy. On the right is our pre-train policy. And what we see is that the pre-train performance looks quite similar, right? They kind of both are doing reasonable things, but not actually able to get the corn in the pot that frequently. Now, if we look at the fine-tuned performance, what we see is that our policy, we're able to significantly boost the fine-tuned performance, while the BC policy is still quite difficult to boost its performance. Okay. So it doesn't succeed every time, but we're kind of getting to the point now where actually we're succeeding like 70, 80% of the time with our policy, while the BC policy is still at like less than 50%. Sort of more quantitatively, we kind of see the same pattern I showed you. Okay. Pre-trained performance is similar, fine-tuned performance of our approach is significantly better. Okay, so the idea here again conceptually is that rather than just doing kind of the naive thing, fitting a policy directly to the demonstrations, we need to take into account kind of our uncertainty based on the demonstrator, and we can see theoretically that gives us some optimal trade-off, and then practically this actually gives us sort of capabilities in terms of fine-tuning pre-trained policies that we maybe wouldn't have otherwise been enabled. Okay, and so sort of just to close, what is RL theory? Sort of going back to this question I framed at the beginning of the talk, what does RL theory have to do with robotics? I think it has a lot to do with robotics. Right? If we think about the problem right, if we formulate the problem correctly, we can take the insights we might get from approaching this in a more sort of algorithmic or theoretical sense. We can derive algorithms there, and then we can deploy these algorithms in the real world, and they actually can enable capabilities that we maybe would not have gotten to with more naive approaches. Okay, so that's kind of where I wanted to leave it. Yeah, happy to take any last questions.
Let's all think this through.